And thanks for the invitation to speak. I'm titling my talk as Power Grid Optimization using limited data, using the power of this guy. So anyone knows who that is? Anyone? Any guess?
Is it Bayes?
You're actually right. It is Bayes, but just like most of his theory, nobody really knows if that's his true picture or not. So according to Wikipedia, it is, according to some historians, with high probability that is said, but it's up to debate. So we'll talk about how do you do optimization or even risk estimation in power systems when you have limited data and at least some aspect of the things. It's probably my first talk at MIT. So just briefly, I was at Los Alamos National Lab, which is a DOE lab in New Mexico until very recently. And I did most of my almost all of my graduate education in Southern US, in Austin, and then I moved to Los Alamos for my postdoc. I primarily work in 3 different areas, though they're related. One of them is in secure grid sensing for estimation detection, a lot in distribution grids. And then I do a little bit of work in understanding how to aggregate resources, particularly behind the meter resources in distribution grids, so that they can do, you can aggregate them to provide different kinds of grid services. And finally, what I'll be speaking on here is some recent work or some aspect of work I've been doing in understanding data-driven augmentations to optimization in bulk grid or large transmission grids. Now, we all know, and probably it's like the crowd here definitely knows that, there has been in recent decades, there has been kind of like a seismic change in the way the power grid in several parts of the world is being operated. Traditionally, the power grid that you had was kind of like this. It was mostly passive. You had large generators that used to serve most of the load. The load was mostly constant. It was not active or flexible. What has happened is we have moved more towards a cleaner, greener grid, where you have a lot more renewables and stochastic resources as generators. You also have a lot of smart devices in terms of loads. So you have electric vehicles, you have household solar, you have smart air conditioners, loads which can be changed. All of this is very good in terms of for the environment and otherwise. The problem is if you have more intermittency or stochastics in the system, there are questions with regards to stability or making sure that things work out as we plan for. On the other hand, recently you also have started doing a lot more measurement collections and data collections in different aspects of the power grid, at high fidelity. And there is a scope that you can use some of those measurements that you've been collecting to devise novel, faster algorithms to optimize and solve the grid that can kind of benefit from all those smart resources that you have in the system. And why is this important, by the way? There's a requirement for developing faster, but again, risk-aware novel algorithms for doing decision-making in power grids. In recent years, there's also been, evolving climate change and other aspects of it impacting the US power grid. There has been, for example, this is a picture of the KPI index that, wildfires have become more common in, at least in the US power grid's footprint. So when you have this kind of extreme events become more and more regular, what needs to be done is you need to develop newer algorithms and hopefully with some guarantees that those algorithms actually perform as they're supposed to. This slide was prepared a few days ago, and yesterday, this is what came up on New York Times. So things might really change in the next few months, but let's hope that they don't much, okay? So all those plots of where solar and all are going might change, but whatever. We can hope for the best and go ahead. As I mentioned, in this particular talk, I'll be focusing primarily on understanding optimization in transmission grid. So for someone who may not be aware, the power grid hierarchically is divided into transmission grid and distribution grid. Transmission grid is this part of the grid. This is the high voltage part, which connects your big, energy generators to kind of your distribution substation. And then beyond it comes what is known as distribution grid. This is the part of the power grid that you see close to your home or close to your office and so forth. We will be focusing primarily on this part. Okay? By the way, feel free to ask questions at any point. Now, one of the things that is done regularly or frequently in transmission grid operations is we solve this problem known as optimal power flow. So what optimal power flow does is it tries to minimize the cost of generating power so as to serve the available load in the system. Now, given this is a physical infrastructure system with its own rules and regulations, you want to satisfy your injections and demands, but you do have technical constraints that you need to satisfy. So it is not just a supply-demand matching problem. There are network constraints that have to be ensured. Mathematically, this is how the problem generally looks like. You are trying to minimize the cost of generation because you want to operate the system at the lowest cost. There is phase in the system. This is the nonlinear AC power flow equations, which is the AC equivalent of the Kirchhoff's laws, which relate potential or voltages with injections or insertion of powers at different nodes in the system. It's nonlinear, and that kind of complicates things. And then you have safety or resource constraints. So these are constraints which relate to the fact that generators can only operate within some margins. Your transmission lines have finite capacity. You cannot overlook them substantially. And you can kind of complicate and look at more and more realistic kind of constraints, where you can think about the fact that your expectation of the load in the system might change. Some resources such as renewables might not be operating at what their forecasted values are. Some of those constraints might be hard, meaning they have to be satisfied at every single instance. Some of them might be soft, meaning you have to satisfy them at high probability, and so on and so forth. These problems are generally harder to solve, and one of the reasons why it is hard to solve, more so in the paradigm where you have a lot more, variables in the system that you can control, is the fact that this is nonlinear. If you have more other constraints in the system, it becomes messy. It's non-convex and all of that. One of the ways in which, at least in market operations and otherwise, you solve this problem is you make some approximations. Okay, so kind of approximations that you can do is you can linearize the system. This is then known as a DC optimal power flow problem. You can solve that. You can make some assumptions on the kind of uncertainty that you have in the system. So one of the things that people normally do is they assume a Gaussian uncertainty for certain kinds of things. They use a Weibull distribution for wind and so on and so forth. The other aspect or a line of work that people have been researching, including here, is this use case of machine learning to solve this problem. And one of the applications in which machine learning can be used is to develop surrogate models for either subparts of the problem or the overall optimization problem itself. So by which I mean you can probably replace these powerful equations by using machine learning. You can also use machine learning to solve this entire problem, so that you take an input of certain loads and you give out what the generated profiles should be. One thing which is crucial though, given this is a critical infrastructure system, it does have an inherent cost in making sure the system is actually feasible, meaning you can come up with machine learning surrogates, but often you do have to validate or ensure that your solutions actually work. Okay. And we'll talk about how can you ensure that, and what are the potential ways in which validation can be done. Okay. Again, there is a lot of work happening in this area. Most people have some paper on using machine learning in power systems, operations, and optimization. So if you don't see your name here, I apologize already. Right? I've already written it's incomplete. Okay. Now, this is how a workflow for grid decisions generally take place. And if you have, if you don't agree to this, feel free to question it. So every 5 to 15 minutes, this is at which dispatch and other decisions are taken in the power grid. You have to decide what the generator set points are. This is what the generator should be operating at. You often also decide what a feedback policy is, meaning if certain things don't operate as they're supposed to, other resources in the system have to pick up that slack, and that is another policy that you decide. Now, you can possibly use machine learning or whatever you want to solve this problem. But given one potential solution, you have to ascertain if that thing is actually feasible, meaning what you have to do is determine that the different states of the system, which are voltages, line flows, and all that, which arise because of this generator set points that you have decided, what those values are, and if they satisfy the constraints in the system, meaning whatever empirical risk of violation of constraints exists, if it is within the limit of what you are okay with or are willing to permit. Okay. If you're satisfied with it, you stop. That's the dispatch. If not, you have to set back the cycle and continue on it. Okay. Now, this is again with discussion with other people who work in this area. for majority of the problem people do, they work on this part of the problem. Okay? They try to come with machine learning algorithms to solve this problem, but this is equally important. You need to make sure that whatever solutions you're proposing should be solvable, and the risk should be computable in a small amount of time, because after 5 to 15 minutes, you have to again resolve the problem. So generative set point feedback policy, this is what I talked about as the optimal power. Yeah.
So what is it that changes every 5 to 15 minutes in the problem that you show? Which parts of the problem change?
So generally the loads will change, okay? But sometimes what can happen is the system itself might change, okay? So you might have already done in your day ahead planning that, certain loads will come up at certain amount of time, or topology might have changed, so on and so forth. But it generally is not going to happen that you're solving, let's say, 100 variable problem. All of a sudden in 5 minutes, it's not going to become a 600 variable different problem. It is going to have some amount of history attached to it. And that is necessary. I mean, that is kind of used in the way we solve this problem.
What are the stage variables?
So in this particular case, I'll be talking primarily about voltages, but then you can have other variables which arise from voltages, like for example, flows and so on and so forth. Okay. So there's this problem of finding the generative set point, maybe using machine learning. It is optimization with non-convex, nonlinear constraints. It has to be solved fast. And often what can happen is, because the system might change, you might not have extensively large training data to solve this problem if you're using machine learning. It might be a limited set that you have. Secondly, this problem of determining state variables and understanding the risk of constraint violation. The primary problem is, let's say if I call the states to be voltages, voltages as a function of injections is actually an implicit nonlinear function, right? Now it can be solved. You can solve it using Newton-Raphson or any other iterative solver. The problem is you have to solve to get this risk of constraint violation to be within whatever your confidence or confidence that you require. You might have to solve a tremendously large amount of those power flow solutions. So this is one particular theoretical bound which is there, which is known as Hoeffding's bound. So epsilon is the error, R is some parameter in the system, delta 1 minus delta is the confidence, and M is the number of empirical variables that you have. So what this is saying is, if you want your error to be bounded by epsilon, and you want to say that this error is less than epsilon with a confidence greater than 1 minus delta, okay? So this is how probabilistic bounds come in. With high probability, you are saying the error is less than epsilon, then the number of measurements or number of times you need to empirically estimate something is given by M, right? This is what is known as Hoeffding's inequality. Now, why is this problem bad? Let's say I take a 500 bus system, 95% confidence, which means delta is 5%, okay? If I want my epsilon to be less than 10 to the power minus 3, you can see that M, this should be M actually, the number of times or samples that you have to generate powerful solutions to get this empirical risk, it goes almost as 10 to the power 8. Okay? So it actually blows up very much, which is actually intuitive, right? So if you want solutions with high confidence, you really need a lot more samples. Just like if you want to compute the mean or variance of a quantity and you want it high precision, you have to take a lot of samples. For a finite bus system, if you take just Newton-Raphson solutions, you require 20,000 AC power flow solutions, and unless you have mechanisms by which you can extremely parallelize this entire thing, it can take you around 4,000 seconds, which is a lot of time. Yeah.
Could you say what the errors are? Like, what is the error exactly?
So what error here means is that, let's say you're computing some quantity, all right? Let's say you're computing constraint violation. Now you want to know what is the value of constraint violation is, but you really don't know, because what you're getting is you're empirically sampling injections and loads and seeing what the violations you're getting. And let's say you'll add them up and take the mean. Now to say that the true value, how close is it to the mean? So if you want to say that the empirical quantity that you have computed and the true value is less than epsilon, with a confidence 1 minus delta, the number of times you have to take samples so that you can compute the mean will grow like this.
So these are like voltage, for example.
Let's say, yeah.
Okay, voltage violations.
This can be voltage violations. It can be a function of that also. And that is where the function quantity somehow comes in R. So let's not get into it, but yeah. So it depends on,
Explain us, just like when you say like number of samples and you say like, what kind of samples are we talking about?
so let's say, so let's say you have a distribution of loads and you're sampling from those loads and then you're computing the number of violations that you're getting.
I
Okay,
see.
so how many quantities do you have to compute and average? Yeah.
So is load the only uncertainty you are considering here?
So in this case, let's say I'm saying it is load, but generally this kind of results will hold for any kind of uncertainty.
I guess I was gonna say that, you know, if you talk about outages of power plants and power lines and so on, I guess traditionally you deal with that by defining contingencies and
Yes.
then you check for those, that list of contingencies, right?
So this is not it. So what I'm talking about is that you have come with a surrogate model, let's say, okay, you've come with a surrogate model for solving a problem. And you're saying that this is the policy which I have and it should work. Now I want to verify if that policy really works under this distribution of different things that can fluctuate a little bit. So it's slightly different from, you know, having a contingency constrained optimization where you're saying it should operate under this list of contingencies. Here I'm saying is that you have solved the problem and now I'm going to test if whatever you're solving is actually satisfying the constraints that you said it is satisfying. And for that, you require this many amount of solutions.
But you can't get out of it, out of what Odin is saying.
No, you can't.
You cannot.
Yeah. What I'm saying is that even in that problem, if you had a machine learning algorithm for doing contingency constrained optimization, unless it's a finite set and you want to test it over a distribution, you still have to do this kind of a methodology to ensure it actually holds. As long as it is not an exact optimization algorithm and you're using some surrogate.
I can just ask, can you do better if you know the distribution?
Can you do better? Actually, yes. So this result only assumes that the maximum value of that error is bounded by R. Okay. So if you, let's say, if you know the variance and all that, you can actually do better and we'll go there about how we use that to make it better.
Just to check, so here in the bound, there's M and R. So what are these numbers? They're constant or they're dependent on the grid?
So R is dependent on the function that you're computing. Okay. It depends on the maximum value of that. So so that needs to be bounded. M is the number of samples. This is for one particular variable. Okay.
Okay.
So now if you have, you know, n different systems and you want to make sure that all of those variables are within some bound, it'll go by, you know, you can do union bounds and all that and it'll grow. Yeah. But so right now it doesn't depend on the size of the system as long as you are computing it for one particular variable. This is the standard way in which auto sample works.
So does the like method of sampling matters, and for what system you created this graph, like, and is this like, I forgot, you were talking about transmission or distribution or?
It's transmission. So the method of sampling it is assuming IID samples from.
Okay.
Which means I'm giving you a distribution. You are computing some quantity of a distribution. You are independently sampling and collecting. And I'm asking how many samples should I collect? So whatever quantity I'm computing, I can say that this is actually close enough to what its true value is.
So why this bound is independent of target model?
Why this bound is independent of the surrogate
Like
model?
it should, for different mission, like let's say target model is based on machine learning method.
Yeah.
Bound should be different for different, perhaps surrogates, machine learning methods, no?
No, it actually, so here, if you assume that the variance and all those quantities are there, it can depend. But this is actually out of sample testing thing, right? So it is, you're assuming every sample is either right or wrong with some probability. So the probability will depend on the machine learning algorithm, but it doesn't, the counting is still independent. If you want, you can discuss slightly more on why and how the derivation works.
I guess the surrogate model is embedded already inside sigma, perhaps.
It's embedded inside sigma in the sense, if you have more information. So here I'm not using any information, right? I'm just using that, if you have a random variable which is bounded by R, and your IID sampling from it, how many do you require?
It's agnostic to those modeling assumptions and distributional assumptions.
That is why it is so great, and also hence it is weak. So it doesn't have all those
So
additional.
how conservative is it?
It is quite conservative. I'll come to it at some point. But then if you do not know anything else, aside from the fact that this variable is bounded by something, that's all you can do, right?
Yeah.
Okay. All right. So I will talk about two particular questions. One is, can we design, machine learning algorithms for solving OPF and all of that, again, without contingencies, using limited data, and can we give some confidence and this kind of derive those bounds for it? And secondly, what I'll talk is that can we design, this kind of injection to voltage maps, which are not implicit, but rather explicit, so that we can do fast risk assessment using limited amount of data, okay? And the solution I'm proposing for both of this is in the framework of Bayesian machine learning, which is, using machine learning with the fact that it's uncertainty inherently built in the system. For the first problem, which is for designing machine learning optimization models, I'll talk about semi-supervised Bayesian neural network. This is a paradigm of neural networks which has been there for quite some time now, and there are now nice, packages by which you can do optimization using it.
But in the first, in B, I think we already know from even simple examples that this is non-unique mapping. You
Yes.
have one S
Yeah.
and you get two voltage solutions, and in the general system, it becomes a mess. So what do you mean by B?
So this is all under the assumption that even with those things being removed, say, let's say I take the high voltage solution, let's assume there's uniqueness, let's assume that it is feasible
Okay.
at least. Even then, can you compute it?
Okay,
Yeah.
but I think you should put that
Yeah,
there
okay, yeah,
because
no,
it's,
yeah,
we actually in our group with machine learning, we do
Yes.
our subgroup. That's a typical counterexample to learning, right? Because it's not uniquely mapped.
Yeah. So for high voltage transmission systems though, what people would do is they'll go at the high voltage solution, and that in certain cases they can, okay, I've forgotten those papers, but at some point people are talking about that solution, if you start at the right point, will converge to,
Hard to defend.
okay. For the second part, which is this explicit map, I will talk about network-aware Gaussian processes for this fast risk estimation. I would actually flip it. So I'll talk primarily first about this B, which is the designing of this risk map. And then I will talk briefly, or I'll focus a little bit on time permitting on this Bayesian neural network based stuff for doing power flow optimization, RO. Okay. Now, what Bayesian machine learning does, and if some of you have taken a course in probability, you have this thing known as Bayes' theorem. So what it does is if you compute this posterior probability, given a prior, so you have some information or some model of what your uncertainty of a certain parameter is, you have some data and a likelihood of how that data B is dependent on this parameter A. And then given this data and this prior, you try to estimate what the posterior probability of A is given the data that you have. Okay, and this is a very general way in which we look at updating models when you get more and more data. In this particular case, let's say whether it is a neural network or something else, you can assume okay, you have parameters in the system W. You have label data, which is input output. This can be, let's say, loads and injections, loads and voltages, but not. You have to estimate what the probability of this parameters W is, under the assumption that there is a model by which you know how output is related to input given the parameters, and some prior on what the distribution of parameters are. And once you have this posterior distribution, you can then find out or give you can model the probability of what the output should be given a new input X, right? So because your parameters themselves follow distribution, what you'll do is you'll say, all right, I have this map of how the output Y looks like given an X and the particular value of W, and then W itself follows the distribution, and I'll then average it out. This is in a very short slide what Bayesian framework of doing optimization or estimation looks like. Okay. Now this Bayesian paradigm it is used in neural networks. You can talk of how people do regularize linear regression, all of that. They're all related to this Bayesian paradigm. There's also this entire area of kernelized regression or nonlinear regression, which also follows from it.
You mentioned framework of estimation optimization. Of what optimization?
No.
Estimation.
This is actually estimation. Yeah. So, but yeah. So you're estimating. So there are parameters in the system that you do maximum likelihood.
Yeah.
And then you kind of do. So there is optimization problem part of it, but you're technically estimating. I mean, there's a phrasing differences there. Okay. Now coming to the first part of the problem, which is you have injections, you have voltages, you want to learn this linear map, or not linear map, you want to learn this explicit map, right? So this is implicit, we don't want this. Now, what is a good approximator? One of them, it should be explicit. So I can then, if I'm given 10,000 samples, I can really compute them fast. Evaluate should be easy. It should be differentiable. Hopefully, should have some insights of the network or our insights of how power systems operate. And again, hopefully, it should be easily retrainable or transferable. So as you mentioned, if the system slightly changes or the load changes, can I then retrain it fast enough with some little bit of extra data instead of starting from scratch itself? Okay. So one of the models that we decided to look for this modeling, this explicit injection to voltage map is this framework of Gaussian process regression. Because a Gaussian process regression, if you have never heard, it's a non-parametric model of relating variables. It kind of relies on this assumption that, let's say V is a function, voltage is a function of injections. There is linking to it to, this Bayesian regression, but it's actually easier to understand this way. You can assume that the voltages for different injection values are correlated. Okay, so let's say that the voltages as a function of injections are random variables, and the voltage given two different injections, their corresponding voltages have a relationship that they're correlated according to a kernel function which maps the distance between the injections. Okay, and one of the ways of modeling a kernel function is this squared exponential kernel. So all this is inherently saying is that if I give you two injections, and these two injections are very close to each other according to some distance which is modeled by this kernel function, then the corresponding voltages for those injections are also going to be close. Okay. On the other hand, if the injections are very different, the voltages are also going to be different, and the difference is kind of modeled by the fact that the correlations will be very different. Right? They're not going to be strong to correlate.
Just a minor question, not a, so maybe it's tangential to Maria's question. Is there a refinement of this theory to have a set of possible voltages that can be induced in this kind of a way of looking at approximation? So set valued kind of a thing rather than, so instead of V hat equal to this, is there a kind of a refinement where you have a set of possible inducible voltages from those injections and then trying to measure the distances between those sets?
I actually haven't looked at it,
Okay.
but I would be surprised if there is, because I mean, there are negative results about, there are kind of counter results to the fact that there actually can be multiple voltages corresponding to the same injections. So I wonder how this will go there.
I'm not sure if the GP theory works for
Yeah, that's what I'm saying. If you don't make those assumptions that, there are uniqueness and all that. Yeah.
Actually, there are simple examples. So if you look at the injection, there is one high voltage, one low voltage, but that bifurcation point where you go from.
What
high
I'm
to
asking
low.
is whether this non-parametric approximation approach actually admits that kind of set of solutions.
No, because the bifurcation point may be in the set that you don't expect. Maybe.
No, but there could be ways of approximating it using function approximation results. That's what I'm
We
asking.
can talk it offline.
Yeah, I would be surprised though. It will require a different kernel. I
Different
think
kernel,
so.
yeah.
So that may be possible.
But it's a valid question to
Yes.
ask.
No, you can talk of different kernel functions in a normal regime, different kernel functions where it is actually very close to instability and all that, where distances are very, I would say it's very minor distances really impact your voltage settings.
Oh, no, that is.
Okay. But generally, this entire function of Gaussian process, it's also one of those universal approximators, just like neural networks are. Meaning, if you get sufficient number of samples, you will be able to approximate it pretty well.
Just a clarification, is that like V is a vector and it's vector function one by one, or what is that function?
So this, you can have vector functions, but let's say right now I'm calling it
One.
voltage,
Okay.
right? So voltage at every, I can model, let's say, every single voltage as a separate Gaussian process. Okay. And this is like a normal map of how it will look like. It is x sin x, your observations at certain points. So the Gaussian process exactly matches at those points, and for others, there is uncertainty in it. One advantage is this is still Gaussian, right? So given this Gaussian, we very clearly know if I already have some data, if I get some new data, how this conditioning looks like. So I can find out, given a new sample, what the mean given a new injection sample, what the mean voltage should look like based on a model, and what the variance or the uncertainty of the model looks like at that particular voltage. Right? Like for example, in this case, if it is very close to this point, which is where a sample node is, if the next injection comes around here, my uncertainty in the function of voltage is small, whereas if it is at a point which is further away from all training data, I'll have large uncertainty in the system.
Would that be would all other points be held constant in that case? So I guess what's on the X and Y axis there?
So this is a simple linear function. So you're doing X sin X.
Okay.
You have certain training data, and then you learn the Gaussian process using something like maximum likelihood. And now given a new point of injections, which is X, let's say if you have to write what Fx should look like, it will come with a mean value based on this formula, and also come with your measure of your confidence or what the variance, estimated variance of the model is at a particular point. And the variance will be large at points which are further away from your general training data. All right. Now this is a very vanilla Gaussian process, meaning I have not incorporated anything to do with power systems here. I've taken power system injection data, I have learned the system, I plotted it. Works incredibly well actually. So if you look at this is 500 random trials on a 500 bus system. You can see that with 100 training samples, you are already in 10 to the power -2 mean absolute error. Okay. Parikshit, who was the postdoc, was kind of leading this project. We all talked about it, and we decided that 10 to the power -3 is a good, a good accuracy required, because if you're looking at 10 to the power -3 per unit error in voltage would be like 1 volt in some sense. Do note that this Gaussian process, estimation process, includes an inversion of a matrix, okay? And it scales, this matrix size scales as, matrix inversion is n cube, where n is the number of samples which is used in that particular Gaussian process. Meaning 100 is fine, but 200, 300 is actually, you're inverting a 300 times 300 matrix, which is large, and you want to avoid it. So we tried thinking, is there a way in which you can improve this model, okay? So what we decided is that we came up with the fact that instead of having network agnostic kernelized functions, we talked about additive kernels, which builds upon node neighborhoods. Okay, and I'll tell you why the intuition for this came about. Generally, we know that a voltage at a particular node depends on injections everywhere. A lot of the dependence actually often happens in its neighborhood, and the fact that two different nodes and these injections will impact the voltages here. But if you go at nodes which are further and further away, I would say their dependence or their impact on that particular voltage will be kind of uncorrelated or independent. Meaning, I'm saying this node here and this other node here, the injections will impact the voltage at this node, but those impacts will be independent. If that is true, we can think of a way in which you can design this kind of kernelized functions which builds upon node neighborhoods. So what we ended up doing is that instead of building one gigantic kernel which takes all injections, we said, all right, look at the voltage here. I'll look at first one kernel which takes voltages, injections at the node neighborhoods. I'll take another kernel which takes, the injections in the neighborhood of some other node and kind of build up to it. Now, we did not look at further details of it, but the hope was that initially, if it is a very large system, you can kind of build this node neighborhoods, and at some point you can kind of terminate it and say, all right, this particular hops in the graph is sufficient for me to model voltage as a function of injections. Okay?
So what is capital B?
So capital B is a number of kernels that you're taking in a system. Okay. Effectively, what can happen is that you're limited by the diameter of the graph, right? So if you go B hops, you'll actually lead to the end of the graph. Each subkernel is also having low dimension now because it's limited by the size or the maximum degree in the graph. Okay.
So do you specify these parameters or do you learn these things? The
The
number
B-
of hops and the number of kernels and.
So we actually took all the B, right? So we actually took the full system. The only difference that you're doing is that by making it based on node neighborhoods, each individual subkernels are actually small in size now, right? Just using that, it actually leads to significant improvement, up to trisets improvement even for the, yeah.
Just to couple. So here we have KV. So this KV is the summation of several squared exponential function, right?
Yes.
Oh, I see.
Yeah. But each kernel is small.
So do you know the B? So do you know how many bases you are using?
Yeah.
Or-
So if you use if you go through the entire system, the B is going to be the diameter of the graph, right? Because if you take B hops, you are actually at the end of the graph in some sense. But the hope is that if it's a large enough system, you should be able to limit at some point.
Yeah.
With a desired accuracy, and you can build on it as well. So with this, additive kernel, you can see that there is a reduction in the size of the maximum absolute error that we get in modeling voltage. There's also a higher accuracy in variance, in the sense that the predicted variance is also lower, okay, which is good. So we're more confident in the model.
What is the intuition of the reduction of variance?
Okay, this is all empirical though, right? So, but the intuition again is that, first of all, if there are low size kernels, the training actually is better because it is additive instead of, it's kind of like you're adding smaller matrices and inverting instead of inverting a gigantic matrix. That's one. The other thing is the impact of local nearby nodes is higher. Additionally, what we figured is that because it is this nice additive structure, we can also do something which is known as active learning. So till now, when I'm talking of Gaussian process learning, what I'm saying is you collect these voltage injection samples and you learn the voltage over whatever many samples you collected. Instead of that, you can do active learning. So you can collect a small set of samples, you learn, and then you pick the next sample based on which maximally improves the model that you have. And again, for Gaussian process, it is actually pretty straightforward. One of the ways in which you do it is by maximizing information gain on variance. Meaning, the next sample that you pick to add into your training data should be one where the variance is high, meaning you do not have much confidence in it. So if you pick that in your training data, the overall system's variance is going to go down. Now, finding this, this injection, which is going to reduce this maximum variance is, again, it's hard and complicated. But because it is, a sum of different kernels, we came up with a simple algorithm for doing it. So what we did was, you find the maximum value of injections at one particular node to reduce this variance. It impacts only a few set of kernels. You fix that. Then you go and find the injection at some other node, which minimizes variance, and keep on doing it. Okay. And this simple network swipe, learning in a way, again, because the kernels are additive, scales fairly well. In fact, to solve it, you don't have to really optimize. You can also do numerical optimization, meaning you can randomly throw points, pick the point which is giving you the highest variance and all that.
So at each update step, I have to do a network swipe.
Yes. But you can, but it is still numeric, right? So you can do it fast.
Can I just say something? I think actually what happens on the large systems, Saurabh, is the response is localized. We change something and it doesn't affect too much. But by the time you take the constraints on Vmin and Vmax, it teaches you when you do the optimization that you have to pick something, who knows where, in order to find the solution. So if you change one at a time within all the constraints, that's fine, right? And there is also a little bit discussion there, but I think the real problem comes when you really want to run this AC OPF is that you have to sort of find like needle in a haystack. Which one is the limiting constraint? And that just destroys localized response thinking. And I'm just wondering, so this is not...
This is actually power flow. It's not even,
doesn't have constraints.
Yeah, it doesn't have constraints. It's just power flow.
Yeah.
You have already solved the problem using some surrogate model. Now you're saying, all right, these are the injections, change the load a little bit, tell me what happens to the power flow equations.
And how are we going to go to optimization then?
No. This is basically.
So in the workflow, this is the validation step. Which step is this in the
This is
workflow?
this. Determining state variables for uncertainty variations and then saying how many constraints get violated.
Sorry. What did you just say?
So let's say you have a generator set point and a feedback policy. And then you're saying that now I'm changing load, I'm changing injection based on a rule that I've already decided. Get the samples, generate those state variables, and tell me how many constraints get violated. So there is no optimization happening right now. Right now it is almost a rule-based.
But the constraints, sorry.
The power flow
The assumption
constraints?
is the constraint is still affected constraint is local, but that's not true necessarily. That's what I'm trying to say.
Yes.
Because the bounds for different constraints are very non-uniform.
Yes.
And so how do we deal with that?
So that is true when you're doing the optimization problem, right? This is more saying that you have solved the optimization problem somewhere, you have come with a policy. So now what is happening is you're changing the inputs and you've already decided a policy based on optimization problem you've solved. You're changing the output based on a policy itself, and you're running power flow equations.
So you are just evaluating which constraints are violated now.
Yes, I'm just evaluating. I'm not imposing the
So
constraint.
there is
Yes.
some decision that has already been done and is just trying to evaluate which constraints are violated or not.
So it's just about power flow calculation, right? It's
Yes.
just power flow.
No, all I'm
There's
trying
no
to say
OPF.
that the
Yes, that's an
power flow,
yes.
the constraint
There
is
is-
not
there's no
local,
constraint.
is not local. That's what I'm saying. And that really kills you again on the way.
That is true if you do it for the entire system, actually.
Yes. that's
But
what
but
I'm
let's say
talking-
if I give you a solution point and you're fluctuating around it, then it is actually local.
No, you may have some far away that it's very little change, but it's you were almost at the limit. And you see that in large scale systems all the
So
time.
just trying to think out loud based on what Maria is expressing, is this approach actually suitable to try to understand the effect of small perturbations on so the point is that, let's say if you're perturbing something at one node, it might be that the constraint at some other node is violated.
Yeah.
Yes.
Far away from that.
Yes.
Right? So is this approach of, so the question is, if I can translate, is this approach of evaluation of constraints, can it identify those constraints efficiently?
It actually does. So there are definitely variables where you observe that, you get a lot more samples in a sense, meaning the model is more, it's not local enough. Okay. Or the fluctuations are large.
What does it mean with regard to identifying those set of constraints which are far away from the location of perturbations? So you're responding in terms of the amount of uncertainty which is required, right, to be resolved.
Yes.
But does it have any mapping to the constraint violation far from the location of the perturbation?
That's the problem.
That I don't know.
That is the
Because
problem.
that we are on modeling, and that actually is not modeled inside powerful equations also.
No.
Yeah, but what I'm trying to say is that can this approach be evaluated to answer such a question?
You
Can it
don't
be
see
used?
that constraint with localized
So it's
assumption.
just evaluation, right?
It's
So-
evaluation. So for example, let's say there is no optimization or whatever, right? Then in a sense, it is modeling, if you take a second order or a linear model, it is modeling kind of a sensitivity of just the powerful equations, okay? Now, what will happen is that given a different set point where, because of the way constraints are, it has changed this kind of, this sensitivity. Your Gaussian process is going to identify that, okay, this thing is more sensitive.
More sensitive, yes.
More sensitive to injection somewhere else.
Yes.
That's all.
But it's going to identify only under localized assumption.
Yes,
And otherwise, so you're not going to see
Yeah.
that far out one.
but what
That is the fact.
But what I'm trying to say is that this model is already inherently assuming that you have decided the injections and then you're fluctuating in its neighborhood.
See, even under small perturbations is fine. I mean, even if I understand that the problem that you're articulating is far more important, right? But even under small perturbations, if it is possible to identify,
Yeah, okay,
even then it's somewhat useful.
Yeah.
okay. that's
Yeah,
fair.
but it does not. So the hope again is that it will not operate if you take injections and loads in the entire domain. The hope is that you have already decided in this tiny region where injections have already been decided. Now you're changing, or generators have already been decided based on the way you think constraints need to be satisfied. Now you've forgotten about the constraints. You are just looking at powerful equations and saying, I'm changing injections, I'm changing loads, and looking at how voltages are changing.
I think we should take this offline, but there is a lot of literature from like 20 years ago before machine learning.
Yeah.
People introduced this notion of concentric relaxation, which means, I have the change here and, because of that, I'm just affecting a little bit.
Mhm.
That's only true under certain assumptions, not always true in power systems. And then from there on, the issue
Yeah.
propagates.
Yeah, that's
I'll share the.
but it should show up in the samples. It should show up in the samples when you collect.
Yeah,
the
so
samples.
that is the key, benefit of such an approach, that the amount of uncertainty that shows up in this GP is reflective of something.
Yes.
And that information could be useful.
Okay. All right. Okay, going fast now. So you can do this network swipe active learning based approach. You can generate more samples and learn this system. And it performs well. So for example, if I use a DNN or something, I'll require 1,000 samples to get an error in 10 to the minus 3. Whereas with this voltage vertex-degree kernel, which is this additive kernel system that we have, with around 50 samples, we are able to get similar kind of errors for a 100 inverse system. If you're using active learning, you often require slightly less than that. It's not clear here, so the average error is almost same, but often your predictive variance or your confidence in the output is improved. So you get less spread, even though the average is still the same. This is also true for a 500 bus system. And now, okay, so this GP based kernel often works well, all right? So what is the use? So what the use now is that if I can learn the Gaussian process based surrogate model for power flow as an explicit function of injections to loads, injections to voltages very fast, what I can do is that, let's say I learn the Gaussian process. Now, instead of sampling from the true power flow equations, which will require solving Newton-Raphson, what I'm going to do is I'm going to sample from the Gaussian process. And now that process is going to be really fast because it's explicit. I can actually sample a lot more than what is required under the Hoeffding bound and all that. And I will use that to estimate my risk, okay? Now clearly, and this is a theoretical result with some assumptions, what it implies is that, if you do risk estimation from a surrogate model, your risk error will have two terms. One is the fact that the Gaussian process itself will have some error from a true model, all right? And the next part of the error is the fact that whatever quantity that you are trying to compute empirically from the Gaussian process will have an empirical error just because you have finite number of samples, right? So it'll be a combination of both these errors, but you can write it out clearly what it looks like.
So where is the first source of error embedded in the result?
So first source of error is coming from the fact that, this under the assumption that the voltage will satisfy this Gaussian process assumption, you will have this Vs minus Vs hat.
So where does it show up in the result?
So it comes in EM 1 minus delta K, which is basically saying if your Gaussian process is wrong, there is definitely an error. Or with high probability, if the Gaussian process is correct, now you have this other part of the error. So delta K is the probability that the Gaussian process is correct. And then you will have, it is bounded by M and then there is this EH, which will come out like that. Okay? So it is pretty clean and easy. The advantage though is for a 500 bus system now, it was taking 4,000 seconds. You can take like 4 times the number of Gaussian process evaluations, but it is explicit, so you can directly compute it. You get it done in 30 seconds, which is around the period of time that at least these colleagues at Georgia Tech were interested in solving this problem. Okay, and now if it is fast like this, you can also do it for a large scale system, right? You can take a 1354 bus system, which you take again 3,000 seconds. You can do it in 200 seconds. You can learn.
Who are these colleagues in Georgia Tech? Pascal?
Yeah, so Pascal is I think he has this project under Mysore where he's developing linear and other models of solving generative dispatch. But then the second part of that is that you have designed these rules, validate that our system's constraints won't get violated, right? So there is a student / postdoc working with Dan Mulzahn and trying to incorporate or build this into their their workflow of doing machine learning based solutions to see if it actually works with them.
So I'm getting lost. So is the Gaussian process an assumption or?
Yes.
It's an assumption.
It's an assumption.
It's not validated in the process when you look to the sample.
Not here. So it is like a meta assumption in the sense that you have looked at multiple systems and say that the Gaussian process assumption actually holds true.
Mm-hmm.
Now, provided the Gaussian process assumption holds true, this is the bound on your error. These are a number of empirical estimates you require, and this is the kind of speed up you can get. Yeah. So it does have that. Provided that voltage values actually follow this Gaussian process assumption, then it follows that. Okay? Yeah. Go ahead.
Sorry, the reason these simulations become not as much better as you scale is because there was that O of n cubed process in inverting some big matrix a while ago. Is that the same reason here?
That is there. We require slightly higher number of samples to do it. Primarily that is there because it doesn't scale with a size. I mean, okay, you have to design those kernels. It has a lot more variables now. There's a lot more additions happening, but overall the matrix grows up. Yeah. Sure.
I'm not sure if I'm going to say this right, but does this work only for interpolated operating points, like points that you've tested on?
Yeah. So our testing the kind of thing that we did was we tested on around 15% load changes, and similar in generators as well.
So would this work for unfamiliar like operating points or no?
Unfamiliar within that range. Okay. So I mean, this is all empirical,
Outside
right?
of
So
range,
it is
yeah,
10 to 15% if it is in that regime. But again, Maria can always say, and this is right, that if things are not feasible and all of those things, and Newton-Raphson doesn't converge and there is the power flow doesn't even exist. This is all. I mean, you can write a theoretical statement around it, saying that entire ball of samples where those infeasibilities happen is tiny in probability. So meaning that power flow solutions exist. Let's say the high voltage solution is unique and all of that.
I think his
then
question
go
is more, if I can try to, his question is more related to the fact that if you had some, the title of the talk says small data, right? So
Yeah.
if there are actually some data points which are not available in some region for which there's no information available, still the GP will fit, right, with some larger uncertainty bound.
Yeah.
That cannot be proven, come on.
Yeah, that's my
What?
question though.
That really cannot be
No, it'll give you a
proven.
larger uncertainty bound. It might be
Uncertainty.
meaningless. but yeah.
Meaningless, so
Exactly.
then it's,
Yeah,
yeah,
That is
okay.
true. That is true. What we are showing is that with like 100 samples, with 10% change, we're getting good answers.
But does it also perhaps, the main question, perhaps it can actually provide, small estimates of regions where additional information would be beneficial?
Yes, that is true. In fact, if you change the generator set points very different, let's say you change the cost of generation, all of a sudden one generator is picking up majority of the load, meaning the entire relationship between injections and voltages have changed. You should technically learn a new GP for that. So this is in no way I'm claiming that given any set point and any injections, this process is going to do with 100 samples. It cannot. What I'm saying is that if you've already decided your injections logic or the generator's logic in a changing load and changing generator in some neighborhood, so that things are still more or less local, this model works very well. Okay. All right, it's almost time, but I'll briefly talk about what I wanted to say in the second part. Okay? Give me 5 minutes. Which is about, so this is about learning this map. The second part is actually learning, can you do machine learning optimization using limited data? And again, in this kind of Bayesian paradigm and why we are interested in it, right? So normally when you talk about machine learning proxies for optimal power flow with, we are interested in the framework where you have limited training data and you have limited time to train the data as well, okay? Because often what people will do is that they would say we have limited training data, but we have unlimited time for training. Now it actually begs the question, if you have unlimited time for training, maybe you should generate training data instead of training your model and then learn your neural network first. Okay, so this entire paradigm is important, how much amount of total time that you're requiring in training data, testing data, as well as the training time. This is the OPF problem. I'm going to abstract it out and say it is minimization of a cost within some linear equalities and inequalities. Okay. So normally the standard machine learning proxies, which is a deep neural network and GNNs and all that, they normally give you point estimates. So given one particular input, you will get one output. Okay? And the way you train it is using maximum likelihood. You can use L2 error. You can use loss entropy and so on and so forth. They either require high training data. So if you're kind of modeling a black box or a gray box model for relating loads all the way to your generator set points, you require a lot of training data, or you can get by having more training time. And one of the ways in which a lot of people, including us, and others, have been trying to do this problem is kind of putting in constraint satisfaction in the loop of training. So what you do is that there's the neural network, you have some input, you get output. All of a sudden, to ensure that constraints get validated, you put your output and input into a power flow solver or under some surrogate costs. You kind of estimate your constraints and variables. If they are not satisfied, you use these errors in your constraint satisfaction or the violations of your constraints into the gradient descent algorithm that you run in updating the weights of your neural network.
What happens if power flow crashes? If the solver crashes?
Yeah, so that we have not gone into. So all I'm saying is I'm saying that set where things don't work is tiny and I can put it in 1 minus epsilon something.
Do some relaxation.
No. There are ways. So the sort of the basic idea, I have actually startup that is based on that. So you will find what are the most effective adjustments to find the power flow
Okay.
solution. And that's the only way. So you solve the power flow, which is analysis, through optimization, looking at Lagrangian coefficients and stuff like that. And this has been a real success story on large systems. So we can talk about that.
So people who do this for neural networks though. So what they would do is that during testing, they get a solution and they would pass it through a correction step, which is kind of saying that, right? So you still have to solve the optimization problem, but you get one particular set of injections of voltage or something, and then you try to project it in the nearest neighborhood in some sense, such that it is a feasible solution, or you try to find a feasible solution. The problem in this is fine if I'm giving you one possible solution to solve, But let's say this module is going inside a planning mode problem, right? Then kinds of getting hard, right? So if you're solving that under every gradient step of your master problem in this inside problem, you have to do this correction step, you have to connect to another powerful solver. There's also machine learning training happening at the same time. It kind of is, it's not clear how to do it fast enough. Okay. So generally you do have a correction step. Okay. So some kind of projection, or what you can do is if you don't really require an exact feasible solution because it's an inner problem or let's say a planning problem, you require enough amount of test data to certify feasibility. Meaning you have a machine learning algorithm, all of a sudden again, change your inputs over, assume that it's coming from a distribution, generate outputs, compute, how many infeasibilities happen, and then give if we can use Hopding or someone and say that, all right, I have with X% confidence, I can say this system generally has this much amount of feasibility, or this much amount of constraint violation and so forth. Okay. So what we decided to do, and I'll go really fast, is we thought, how about making it a probabilistic solution? Okay, so let's say this goes into some other problem. We want to not just give you an output, we want to say, all right, this is the output, and this is the kind of confidence that I have in the output of this machine learning algorithm. Now that can be done. So one framework by which people do it is called Bayesian neural network. A simple way to understand what a Bayesian neural network is that instead of having fixed weights, the weights of the neural network are themselves now a distribution. Meaning, I don't say the weight at every value, biases and all are fixed. They're coming from distribution. So at every iteration, if I want to run the neural network, I will sample from each of the distributions and get one possible output. Now you ask me something else, you sample again and get different output. Okay. In some sense, this has become kind of like a generative model in some sense, right? So given a particular input, I can give you different kinds of outputs based on the distribution which I have. Now, if it is able to learn this distribution exactly, your posterior should, if it is perfect, it should become, delta. It should take all its probability in the right amount of size, so you get very realistic solutions. Okay. How do you do it? This is back to what I was talking about in Bayes' theorem, with posterior based on prior and likelihood and all of that. So all you do here is, you have load, you have generated voltages and all that. Let's say you have labeled data. You can write a likelihood function, which is saying, okay, your generated voltage is a function of the weights of a neural network and your input. You can define this, and you can write a posterior based on your likelihood as well as your prior of weights for your Bayesian neural network. Okay. So now again, you'll get a posterior. This is again a distribution. Now, once you've learned that, and there are modules and packages to do it, given a particular set of input to compute the output, you will sample from this distribution and get one possible output of what your what the output of the OPF should look like. Okay. Now, the regime I'm interested in is there's limited training data, right? So I cannot assume that I can, with this limited number of training data, the OPF actually learns exactly. Okay. So what I'm going to do is I'm going to generate unlabeled data, which is not going to do anything with respect to a cost, just to model these constraints in the system. And I'm going to design a new cost, which will depend on the equality gap and inequality gap. All it is saying is that this part of the machine learning algorithm is trying to enforce that by reducing the equality and inequality gap, it is going to make solutions move closer to feasibility. Okay. So I'll take this data, I'll construct another, likelihood, and I can do one more Bayesian line, so that while for label data, I'm trying to match exactly what the output, two output of those samples are. For this unlabeled data, which I've generated on my own, I'm trying to make sure that I'm trying to kind of coerce the machine learning or the Bayesian learning algorithm to move towards a regime where the feasibility is enforced. Okay. This is, again, going very fast. So you have this problem, you're trying to minimize the cost with inequality and equality constraints. You have a little bit of training data. You develop this labeled loss, which is trying to match the true label. And then you have this unlabeled cost, which is unsupervised, which is trying to say that, okay, this is the cost associated with constraints. The true value should be 0, and trying to move it towards that. This regime is generally called semi-supervised. Okay, so it's part of it is supervised, part of it is unsupervised. And then we train this Bayesian machine learning algorithm in this sandwich fashion. So what happens is, you first of all take a supervised step. You try to find weights which try to match those values. And the next step, you start off with this, this a posteriori distribution of weights as your input, take it as your prior. go towards the unsupervised step. Try to push it towards feasibility and continue with it. Eventually, you will end up with a distribution of weights that you are okay with. And then to predict the output from this Bayesian neural network, you are going to sample weights according to this distribution, pass it through the take those weights for the given neural network that you have, get a potential sample of what the output should be. Okay?
So what's the conceptual link with this Priadontis DC3 paper?
So Priadontis DC3 paper is kind of doing this, but she's not doing it for I would say she's not doing it for
Vision.
for Bayesian. Okay, and there are slightly some other details about it, like in the sense that depending on
But the way in which she does unsupervised is similar to yours or different?
the cost is similar, but what she's doing is also that she is also she's not predicting every single variable. So part of the predictions, if I'm correct, is happening through a powerful solver. So one thing that you can do is, you can predict all variables, then you have those constraints, you can plug them in those constraints and see if the constraints are satisfied or not. Or you can predict one set of variables, the sufficient number, and the remaining variables like voltages and all that, you can then use a powerful solver to give you those values, and they are going to be exact. The problem is that in training it, you require access to a powerful solver at every single time. And that
Which is what they are using.
which is, I think DC3 is that's what is being used. And that is what we were using in some of our work also, where we were, connecting to Math power and then getting voltages out of it. It actually works really well, but the problem again is often what happens is you are using a Python package for doing it, and then if you're training, you're doing batch learning, but again you have to do power flow for every single sample in parallel, and it kind of slows down the system. On the other hand, this is what Pascal and a few others were doing was they generate all the variables, and now you don't need a solver. You just put it in you plug all those variables in those equality and inequality constraints and see if they're satisfied or not. Okay. One particular thing I'd like to highlight is that this is actually a random neural network, right? So your weights have a distribution. So to generate the value or your predicted output, you can sample it once, you can sample it however many times you want, and then find the average quantity and give your average prediction as well as the variance. Okay. In fact, we decided if you really have this kind of a random generator, why should you find a mean? Just sample multiple times, get different outputs, and find the output which is more feasible, more accurate, and pick it to be a solution. Right. So you can always do that. Not very dissimilar from how these GANs and all work. So you generate all of it and take the best solution. Second last slide. It works fairly well compared to deep neural networks and other architectures at low level samples and training data. So we are looking at the gap from optimality, how much of the equality gap is broken down, mean equality, inequality, etc. 5718, the paper also has larger test cases of 1,000 and 2,000 bus systems. Again, under very strict conditions though. We have only 600 seconds total for training. We are taking 500 labeled samples. Unlabeled samples, you can do whatever you want because it doesn't really take much time. And we're using this package from AI for Opt from Georgia Tech to generate it. This is again all solutions without any corrective step and all that. So it is actually performing really well, and corrections will only make it
How
better.
do you get optimality gap?
Oh, this is by looking at test data. So you get your solution, and then you look at a standard AC OPF, a local solver like
But
IP.
that is not necessarily.
That is also true. That is, so if you're assuming that a solver may not work, again, I'll get by saying there's 1 minus delta phi will be even.
So
That is
is Pascal's AI Center addressing these questions?
About the fact that there is no
All these questions that we are discussing.
they're addressing part of it, but actually if you look at people who are in that system, generally you do always get a solution. It is certification which is it's a harder thing. Meaning you will always get a local solution which works fairly well.
So I want to make a generic comment because I spent too much time on this particular problem in real systems. Why is that Pascal doesn't run one single real utility problem? Why do we end up at 58 and 118?
I think we are doing it for 2000 bus system though, by the way.
For which one?
For 2000 bus, this Google
Polish
releases
system, Polish system.
Polish system, and Google released some other larger systems also.
So if you go, and I have a lot of experience with utility, you go and they give you their data. Most of these things crash in a hurry.
I won't be surprised. So generally,
So what is going on? That's my
So why is
question.
Pascal not addressing that?
Yeah.
But he's doing it on some, I think he's at least training
No,
on some.
Nobody, no, actually, there is no AC OPF that's being used for utility in the US now.
Okay. I thought he had some data set from MISO, which was large enough that was realistic, and I think that's what was in his presentations.
Is there published that?
I think so.
I would
in
love
some-
to see
I
that.
think what
Really
we
good.
need to do is sometime we need to see whether the kind of questions this ML and AI people are they actually asking the right questions in terms of identifying those adversarial kind of scenarios or non-local situations or.
Yes.
No, that is, so this is my general philosophy is that if you give me one particular system, I should not run a generic algorithm. I should first of all look at which are the constraints which impact it, which are the things which get violated, and then reduce it. And I mean, this is how, at least.
This guy just published in his master thesis that you have to look at the system first, how sensitive it is before you go any further.
No, in fact, when I was talking to all of those people who have got awards in, this ARPA Go competitions, they were all saying the algorithms are fairly simple. It's just that you are using an intuition to reduce the search space and do all of that.
Just to advertise L'Oreal a little
No,
bit.
no,
Yeah,
it's something
the best paper award at Met Power was that.
Maria was first author.
No, but it really was out of master
Oh,
thesis,
nice, that's good.
this is a key, I agree 100%. You get this data that you really don't know how sensitive they are to any changes. And so babying the real world system first so that you do something with it is just a very hard question.
Google's data set, I don't think it is again, it's real. It's mostly power model data sets, and then they are taking for larger test cases and releasing. Okay, final comment. Because it is Bayesian neural network, you can again do something more. Someone had asked about this is Hopkins bound. This is when you have the only quantity that you have is the max value of uncertainty. If you can estimate what the variance of a particular error is, you can actually get by with doing much better. So this is again a bound which is saying you need, with confidence 1 minus delta, the error should be less than epsilon. How many samples? M, but here we have additionally variance. This is known as Bernstein's inequality. With a Bayesian neural network, what we actually showed was that for a lot of systems, this variance of the model can actually be empirically computed really fast. Okay. Now, if you have that variance, what you can do is that now you can get realistic bounds. So what this is saying is this black curve is the real error. Okay. And then based on your empirical estimate of error, you can give a bound. If you use the Hopkins inequality, which is basically just with max value, you get, these are very conservative bounds. It's not impacting based on the buses and all that. Okay. But if you use this theoretical Bernstein's inequality, using this computed variance that you can do using Bayesian neural networks, you can actually get, it's actually quite nice and close to what the curve actually looks like for majority of test cases. Why this is important? It's actually more important in my opinion compared to how close to feasibility it is that you have a measure of what your feasibility boundary and all can be for your neural network model. So now if the neural network model goes into a planning problem, you can say, all right, run this neural network model, but make the assumption that, the errors, the voltages that is going to predict might have this kind of error in its accuracy. So make sure you change your boundaries in the right way so that the solutions give you realistic answers. Okay. That's more or less it. We are doing more testing. We are trying to see how confidence can be used. There's some interest in understanding impact of it in distribution grids where, there's a lot more non-linearity and so on and so forth, estimated data. And one particular talk, which I didn't talk about, is the fact that this Gaussian process-based power flow model is actually surprisingly very robust to topology changes because there's this inherent network structure built into it. If you change the topology, some of those kernels will change, and then with 10 additional samples, you can relearn and really do well. Okay. So that's more or less it. The 3 papers are out there. Parikshit was a postdoc doing some of it. Went back to India to be a professor at IIT, and Sid and Karthik. Sid is actually a MIT CSEL graduate. Sid and Karthik are ex-colleagues at Los Alamos who were part of this work. And I took 15 minutes extra. So sorry about